6.3 sampling distributions and estimators. One thing we're going to be talking about is talking about a sample. And earlier in the year, we talked about statistics came from a sample instead of population or proportions or something like that. Okay. So in general, when samples of the same size are taken from the same population, the following two properties apply. Sample proportions tend to be normally distributed. So there's our normal curve, the nice bell shape. And then the mean of the sample proportions is the same as the population mean. And that's going to come up in your homework a couple of times, a couple of different times. So the mean of the sample is the same as the population mean. We've got a couple of equations from earlier, and we probably won't deal with the standard deviation as much as the population variance. And we're also going to see the sample variance. And one of the example problems I think is kind of confusing, especially since the sample variance, the equation for the sample variance is a lot more complicated than what we need for this example. So I'm going to show you kind of a watered down formula for it, and then I'll maybe show you the general equation, more complicated. I don't think you'll need it. But in general, what we're going to do for the sample variance, S squared, it's going to be the difference squared divided by n. And that's not, I hesitate to show you that because it only works for 2 items. If I expanded it to 3, 4, 5 items, it's not going to work. We'd have to use the other equation. But for this example, that'll be good enough. All right. The next slide, you've got a whole bunch of information, and you can see information about proportions and means and variances, and there's a lot of repetitiveness. All that stuff looks the same. You've got a normal curve and stuff, but what I want to tell you first of all is what they're talking about when they talk about a proportion. When they talk about a proportion, and you probably already know this, proportion is going to be talking about how many you have out of how many there are. It's like part over total, basically. How many you have out of how many there are. And there's going to be an example. Let's call it example 0. Actually, you know what? Let's call it example 4. I know it's weird to do example 4 first, but this looks like example 4 in your homework, or problem 4 in your homework, where it's talking about a proportion. And so it gives you, it talks about childbirths. And it gives you this list of different possibilities that we've seen before. Boy, 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 girl, girl, boy, girl, girl. Just the different possible ways of having 2 kids, I guess. And it wants us to come up with a probability distribution for the proportion of girls. If you don't remember what a probability distribution is, it's a table of all of the probabilities. So you're going to have proportion of girls and probability. And so I think this is confusing at first. It's a confusing way of thinking about it. But remember, a proportion is talking about how many you have out of how many there are, or, part out of total if you want. And so I look at this element of my sample space, and I see there are 0 girls out of 2 potential children, or out of 2 children, right? And so the proportion of girls is 0 out of 2. 0 out of 2 of those kids are girls. We can reduce that, of course, to 0, simplify that to 0. And then I might look at these two taken together, there's one girl out of the two children. I think the Math Excel is going to want a decimal, so that's 0.5. That proportion is 0.5. 0.5 of the children are girls. And then, of course, this item, 2 out of 2 are girls. Reduce that. That reduces to 1. That's proportion. Okay? So then the probability is just there's one element out of the sample space out of the 4 items. That's the probability of 1/4 getting one girl out of 2. There were 2 out of the 4 elements that had one girl out of 2, and then there was one of the 4 that had 2 girls. You've done probability distributions before. You've done a table like that before, but I just think when they give you that proportion and you're not quite sure what they're talking about with proportion, I think it's a little bit tricky. So we know how to find the mean. The mean, you add them up and divide by the number of numbers. And then variance. Variance is the one I think that's the trickiest because it's harder for us to nail down what variance means. I gave you a couple of equations earlier, so keep those in mind up there at the top. Variance, but in general, variance is talking about how much the numbers differ or how much they differ from the mean more specifically. But we're going to have to do different calculations like that and more. Number 1. 3 randomly selected households are surveyed. The numbers of people in the households are 2, 3, and 10. Assume that samples of size n equal 2 are randomly selected with replacement from the population of 2, 3, and 10. Here are the 9 samples. So what they're saying is, imagine if you had like slips of paper, and one slip of paper had a 2 on it, and one slip of paper had a 3 on it, and one slip of paper had a 10 on it. Put them in a jar, pick one out, put it back, pick one out. Okay, so you could have picked a 2 and a 2, or a 2 and a 3, a 2 and a 10, a 3 and a 2. You could have picked these things. Those are the different ways of pulling out those 2 slips of paper with replacement. Those are your 9 samples, and pretty much all of your homework problems are going to look like this. This is the hardest one because it's talking about variance, and it's the hardest formula, and it's probably also the one we understand the least. Okay, find the variance of each of the 9 samples, then summarize the sampling distribution of the variances in the format of a table representing the probability distribution of the distinct variance values. Wow, that's a lot. Okay, basically they're saying make a probability distribution, make that table with all of the variances. Okay, so write really small here because I probably didn't give you quite enough room. Write small, I'm going to use up all of the space. Let's start by just kind of copying the 9 samples. So we had 2, 2, 2, 3, 2, 10, 3, 2, 3, 3, 3, 10, 10, 2, 10, 3, oops. Ten, 10. Okay, since we're finding variance, we're finding that s squared. And, well, I didn't give you the real formula. I just gave you the one that will work for this example. Basically, we're talking about difference squared over n. That's the formula that will get you through this problem with n equal 2. This only works with n equal 2. If n were something else, we'd have to go to the bigger formula. But anyway, let's start with that. So variance is talking about how much the numbers differ. And so that's where I'm talking about the difference. So when I'm talking about difference here, look at these first two numbers and find the difference. The difference, 2 minus 2, is 0. So all I'm going to do is I'm going to take that 0, the difference, and square it and divide by n, which was given to us in the problem, is 2. N is 2 because I'm selecting two numbers. So, use a calculator on these if you need to, but 0 squared divided by 2 is going to be 0, right? We're going to do that same thing all the way across for every one of these numbers, okay? The difference, and it doesn't really matter which way you subtract, 2 minus 3 or 3 minus 2, because once you square it, the negative sign goes away. 2 minus 3 is negative 1, squared is 1. 3 minus 2 is 1, squared is 1. It doesn't really matter, so I would just do it the easy way. Big minus little is 1. You want to square it and divide by 2. That's going to be 1 over 2. That's 0.5. Math Excel is going to want you to enter in decimal numbers, so let's go ahead and change it to decimal. Use a calculator if you need to. Difference of these two numbers is 8. You square that and divide by 2. 64 divided by 2 is 32. 3 and 2, we've already done that one. Difference is 1. You square it, divided by 2, that's going to be 0.5. 3 and 3, well, that difference is 0. Subtract them, you get 0. Squared over 2, that's 0. Next one, subtract them, you get 7 squared over 2. That's 49 over 2, which is 24.5. Next one, the difference is 8. You square it, you divide by 2, that's 64 over 2. It's 32. Difference of 7 squared over 2. Notice you're seeing some repeat, right? That's 49 over 2, that's 24.5. And the last one, the difference is 0. You square, divide by 2. That's going to give me 0. Okay. So we found the variance of each of the 9 samples. Okay. Then summarize the sampling distribution of the variances in the format of a table. So distribution just means how many of each, basically. Okay. And so let's make our table. In our table, we're going to say S squared and probability. And Math Excel is going to want you to put them in increasing order. So the smallest number I see here is 0. And so I'm going to write a 0. And the probability of that, since there are 3 of them out of the 9 different sets of numbers, it's going to be 3/9. And I don't know if you need to reduce or not. When I looked at it, you didn't need to. So I'm just going to leave it as 3/9. I'm going to leave it unreduced. You'll see why here in a second. The next smallest number is this 0.5. So let's say 0.5. I see 2 of them, so that probability will be 2/9, 2 out of 9. We keep going, putting them in increasing order. The next one I see is this 24.5. 24.5. There are 2 of them, so that's 2/9. And then the only one I haven't done yet is this 32. That's 32. And that is also 2/9. Now, one way I will kind of quickly check my answer here before I click submit or whatever, I look at the probability numbers and make sure they add up to 1. Or look at the numerator. 3 plus 2 plus 2 plus 2 is 9. That's going to be 9/9, so that's going to be 1. I think I got everything. I think I'm done with that. Okay. That is your table representing the probability distribution. All right. So before I move on, I want to show you the old or the bigger, more versatile formula. basically, the other formula that you don't need on this problem is going to say you're going to take one of your x numbers um, minus the mean and square it over n plus, oops, plus another x number minus the mean squared. Okay. And if n was 3, then you'd have another one and another one and another one and another one and another one. And so it's not really talking about difference from each other as much as difference from the mean. And so that's a better formula. But when n is 2, I don't really need that big formula because all it's making me do is this. All right. So that said, I wouldn't even worry about it if I were you for now. Part B. Do the sample variances target the value of the population variance? They're going to ask you this question. And when they ask you this question, basically what they're saying is, are they equal? When they say, does this target this, they're saying, is this equal to this? Because if you show that they're equal, then yes, they target. If it doesn't equal, then no. Okay, so we have to talk about the sample variance and the population variance. And that's easier said than done. So when we write the sample variances, I'm actually going to say the mean of the sample variances. Ooh. You've actually seen this kind of thing calculated before. All you have to do is something that we've done before is look back at your table and you're going to say left side times right side plus left times right plus left times right plus left times right. We found the expected value of a distribution table, a probability distribution. So we're going to go 0 times 3/9 plus, that's a 0, 0.5 times 2/9 plus 24.5 times 2/9 plus 32 times 2/9. And we've done that before. We found the expected value of the numbers in the probability distribution. So you would want a calculator. I'm going to kind of skip over that to be quick, but once I plug all that in, I get about 12.67. That's the mean of the sample variance. So now we do the population variance. Because after all, that's what we're trying to do. We're trying to show the sample variance equals the population variance. Okay. Here's where that equation comes in. You had the population variance was the sigma squared equals capital sigma times x, quantity x minus mu squared over n, capital N. Okay. So the difference between capital N and small n is small n up here was talking about the sample. We sampled with 2 numbers, but big N is how many numbers are in my population, and that's 2, 3, and 10. There are 3. So it's a little bit tricky sometimes. You're like, well, why'd you use capital N here and why'd you use small n here? Capital N is the population. There were 3 numbers. Little n was the sample. I only picked 2 for each of the different things. Okay. Mu is the mean. And so when I look at my numbers 2, 3, and 10, mu is just add them up and divide by the number of numbers. That's the mean. That's mu. Going to be 15 over 3, which is 5. The mu, or the population mean, is 5. I'm going to put that down here again. Mu is 5. So think about what your formula said. You've got to do a sigma, so that means you got to do a sum. You got to add up some stuff, specifically each x value. First x value was 2. So when I look right here in this parentheses, I got an x value of 2 minus the mu value was 5, and I'm going to square that. Plus, I've got another x value, which was 3. Remember, our numbers were 2, 3, and 10, right? So I'm going to take that x value of 3, subtract the mu, which was 5, and square it, plus, and do the same thing for my 10. I've got an x value of 10 minus that mu value was 5, and square it, and I'm going to divide by the big N, which was 3. There are 3 numbers in my population. I'm going to let you punch all the buttons in the calculator or whatever, but you punch all that up, you're going to get 38 over 3, which is approximately 12.67. They're equal. Notice that the mean of the sample varies, the population variance, those two things are equal. And so they're going to ask you a couple of questions, but you need to notice that those two numbers are equal. That tells me two things. It tells me that the sample variance targets population variance. And it also tells me sample variances make good estimators of population variance. That's the general recipe for every single one of the problems in this section. Now, the good news is the other problems are going to be easier. Variance is the hardest one. It's got the hardest formula to remember. It's the hardest to remember even what it's talking about, variance. What even is that, right? The next one we're going to do is very, very similar, except in example 2, we're talking about the median. And the median is going to be much, much simpler to calculate. Okay. So it's basically the same question, right? They give you two different, or like 3 other numbers, 2, 4, and 9. Sample is still n equal 2, so that means we're picking 2 of those numbers with replacement. Okay. But this time I'm gonna save some room here. I'm not gonna write down all those things again, because I've got enough room to find the median. Remember, median is the middle. And so if you look at these two numbers, the middle of those two numbers is 2. And if you look at these two numbers, the middle of these two numbers is 3. The median is the middle of the numbers. Now, 2 and 9 is a little bit harder to do in your head, but remember, if you can't do it in your head, you're just finding the average, basically. 2 plus 9 divided by 2, that's 11 over 2, that's 5.5. The median of 4 and 2 is 3. The median of 4 and 4 is 4. 4 and 9. Well, you add those up, that's going to be 13 over 2. That's 6.5. That's 6.5. Right? 4 plus 9 over 2. 9 and 2, well, we already did 2 and 9. That'd be the same thing, 5.5. 9 and 4, we already did 4 and 9. Didn't we? Yeah. That's 6.5. 9 and 9, the middle of that, the median of that is 9. Oops, mistake, 6.5. Okay, so I found the medians for each of my samples, right? I found the medians for each of my samples. That's what they asked me. Find the median of each of the 9 samples, then summarize the sampling distribution. Summarize those numbers in a table. Math Excel is going to want you to put them in increasing order. Smallest number I see is 2. And then I see a 3, 4, 5.5, 6.5, and 9. Math Excel makes you choose the numbers out of a drop down. It's kind of weird how they do it, but as long as you find the numbers, it should be pretty self-explanatory. You want to find those probabilities. Well, there's only one of these 2s, so that's 1/9 probability. 3, I see a couple of them, so that's 2/9. 4, there's only one of them, so that's 1/9. 5.5 looks like 2/9. 6.5, 2/9. And 9, there's only one of them, so that's 1/9. A real quick way to check is make sure all that stuff adds up to 1. You've got 1/9, 2/9, 1/9, 2/9, 2/9, 1/9. Add the numerators. That's 3, 4, 5, 6, 7, 8, 9. I think that's right. I think that's it. Okay. So now I've got in the format of a table. That's what they asked me to do. That part's done. Do the sample medians target the value of the population? So again, they're asking if the sample medians are equal to the population median. Okay, so the sample, that's where we have to do, this times this, plus 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 this times this. When we're finding the mean of the sample medians. And you type all that in and you get 5. All that stuff adds up to 5. And we want to do the population. Now remember, we're finding the median. And our numbers were 2, 4, and 9. The population numbers were 2 and 4 and 9. All you have to do is find the median right there. The median is 4. The population median is 4. I compare those two results and I see that they're not equal. That gives me 2 conclusions here. Sample medians don't target population medians. And they don't make good estimators. Okay, that one felt a lot better than the first one, right? Now it's the same question again, but this time This time they're talking about range. Okay. This time they're talking about range. All right, part A says you have to list the numbers out. So, okay, that kind of stinks, but whatever, we got this. It's the same thing. You've got these three numbers, and we want two of the ages, so n equals 2. We're just going to say, all right, that'd be 56 and 56, 56, 46, 56, 60, or 46, 46, 46, 56, 46, 60, or 60, 60, 60, 56, oops, 60, and 46. It doesn't really matter if you put them out of order or whatever. It's just list out those 9. You get the 9 different ways of picking those things. Okay. So when they say range, it's been a while since we've thought about range as this definition, but range is just the maximum minus the minimum. So you're subtracting them. Subtract them, subtract them, subtract, 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 subtract. Yeah. The range, big minus little. Okay. Summarize using a table. So what's our table look like? We've got range and probability. The different values that the range could take on look like 0, 4, 10, and 14. Probability looks like there's 3/9 for a 0, 2/9 for a 4, 2/9 for a 10, and 2/9 for a 14. Feels like the same problem, yeah? Compare the population range to the mean of the sample ranges. It's the same question, right? So the sample ranges is the one where we have to look at the table. The population is usually just going to be whatever you would do to find the range, whatever formula it would be or whatever. So we're finding the range for your population, and those three numbers were what? 56, 46, and 60. So just look at those three numbers. So your population range is big minus small is 14. That's it for your population range. That's your population range. Obviously, those two numbers are not equal. So we have those same conclusions. Sample doesn't target population or make good estimators. Okay. Now at the end, maybe I should have gone over this slide earlier, but an estimator is a statistic used to estimate the value of a population parameter. Okay, yeah, obvious. And then it kind of summarizes which ones are good estimators and which ones are not. Unbiased is a statistic that targets the value. These do. That's unbiased. And a biased estimator does not target, and that's these. So the reason I didn't do that slide first is because I didn't want to give you the answers before we did the problems. Why sample with replacement? When selecting a relatively small sample from a large population, it makes no significant difference whether we sample with replacement or without. Sampling with replacement results in independent events that are unaffected by previous outcomes, and independent events are easier to analyze and result in simpler calculations and formulas.